Okay. My screen is visible.
Yes, sir, visible.
Okay, good morning, all of you. Today we'll see the second unit, the genetic algorithm. In the third unit and all, differential evaluation and all, there is a different types of algorithms we are going to deal in this, and that we apply to the electrical applications. In this, before going to in detail of the genetic algorithm, we'll see the introduction. What is the sequence to evaluate or to solve any complicated problems or optimization problems using genetic algorithm? We'll discuss. These are the topics in this unit. Introduction to genetic algorithm, encoding, fitness, and then basic operators. We have as different types of crossover operators and different types of mutation operators. All these things we'll discuss in this. And control parameters estimation, niching methods, and parallel genetic algorithms, and genetic algorithm versus conventional techniques. And then we will see the detailed working of a genetic algorithm with an example. We'll consider different examples or objective functions and how to minimize or maximize the objective function using genetic algorithms. These are the total presentation agenda or syllabus in this unit. As you are aware that genetic algorithm is a search-based optimization techniques. So that will work on genetics and natural selection. The frequently used to find the optimal solution or near to the optimal solution to difficult problems using genetic algorithm. So to solve optimal problems in a research or in machine learning algorithms, we are going to use this genetic algorithm. Nature has always been a great source of inspiration to all mankind. So, based on the nature inspiration, or you can say that some of the what you call it as mankind scenario, we are going to implement the problem. This is already mentioned search based algorithm based on the concept of natural selection and genetics. So the how genetics will work that we are applying to solve our problem. This GAs are subset of much larger branch of computing known as evolutionary computation, and developed by John Holland. And in general, another along with his students and colleagues, they developed this algorithm. The genetic algorithm, we have a pool or population possible solution to give the problem. These solutions undergo a recombination, that means crossover operation, and mutation. Like in natural genetics, I will show that what is the chromosomes, genes, and then population, all these things in the upcoming slides. And by doing this process, we can able to get as a new children. Suppose two parents is initial stage, then a new generation is going to be happen. That will be as a new children, and process is repeated over various generations, and the best solution will be carry forward, and then worst solution we can discard. And the fitness values is subject. Once the variables are known, then we can substitute that in that objective function. We'll get the fitness value. Our individual solution will generate. You are keep on doing this up to the what you call it as stopping criteria, and that will be consider initial stage, whether it is what you call it as a number of iterations, or we can consider as a solution range or optimal value. Once if you set that stopping criteria, that point reached, we have to stop the process. And before being to genetic algorithm, we see that essential to familiar with some terminology that we'll see before starting. That's what the introduction will start with any topic. And here one population. So these are all the some of the terminologies are required while we are doing the problem. So in that, one is a population. It is a subset of all the possible solutions to give the problem. So initially, for all the case, we'll start with the random solution. Whether it is a final solution or not, that will decide by later point of time while we are doing the process. But the moment what we'll do is we'll always start with the population as a random solution. So for two variables are there in general, other than genetic algorithm and all, what we'll use is we'll consider as a some random values. You put it into function and we'll get it as a function value, and a later point of time that will carry forward to the next operators, and whether it is a better solution or and the worst solution, based on that it will go for as a next iteration process. In that case, population is a set of all possible solutions. That is the terminology. And now we can see in the case of genetic algorithm, preferably variables, a binary coded genetic algorithm will consider only zeros and ones variable. So we can see that chromosome, this chromosomes is one such solution to give a problem. We have many solutions. Let assume that different chromosomes, it may be any, or you can say that n number of chromosome. This is one solution, this is another solution, like that. You can keep on mention the something, chromosome. All set of chromosomes will call it as a population. So suppose the number of population you can decide by yourself based on our problem. Generally, some all optimization algorithms and all will take it as a 50 population or 100 population. By taking more and more, we'll get as a better solution. That is the reason we'll consider as a population size. Now, by seeing this diagram, the chromosome, this one row of values, this is a chromosomes. In that, we have another genes. A gene is a one element hosting of a chromosome. So these are all the set of, it may be n. Sometimes we'll take it as a n is equal to 3. Sometimes n is equal to 4. N is 5. It depends on the maximum value of the problem. You can see that x minimum and x maximum we have. So based on that x minimum and x maximum, we can easily consider as a what you call it as the n value. Suppose we can consider n is equal to 4, then this some chromosomes we can write like this, that we can easily calculate what is the value of this. That is a these are all binary. Then after that actual value you have to calculate. I will show how to get that actual value also. At moment, first try to understand all these things will be represented in terms of the ones and zeros. So in that case, chromosome is nothing but a one solution here. In that chromosome, we have as a Gini value, and many each position we call it as a Jenny. In that Jenny, we have as a value, it may be 1 or it may be 0, that we call as a allele. So that value we call it as a allele, and that position, each position we call it as a Jenny. So now allele, that's what I mentioned here. Allele, it is the value a Jenny takes from particular chromosome. So this is the total terminology. There is a population and chromosome. So these are the main terminology. We can see that solutions. Suppose if I take four population, means four solutions. This all together we call it as a population. One chromosome N1, A1, and A2, A3, A4, all are the populations. So these are, chromosomes. A1 is one chromosome. This is one solution. This all values ones and zeros only. And in that chromosome, how many chromosomes we have here? Four chromosomes. All together, I call it as a population. It may be A5 also, you can take it, A6 also, you can take it like this. And any number that you can consider as a population. And inside the population, the positions, I call it as a Jenny position. That the value allele. Now, you can see after this, there is a lot of, operators we need to add. One is a crossover operator, another one is a mutation operators like that. We'll see that in the next slide. Now, principle of genetic algorithm. What are the sequences we are going to operate in a genetic algorithm? As I said, population. First, you have to generate randomly within a minimum and a maximum. We'll generate some solutions that we call it as a chromosome. In each solution is a chromosome. That number, if I take it as a some n number of the chromosomes, that we call it as a population. So all the algorithm starts with the population of the candidate solution to optimize the problem. So n number of populations we have to take it. Each candidate solution represents the potential solution to the problem. Another one is a chromosome representation. So each candidate solution is encoded into chromosome, typically represented as a string of a binary bit. That is the population. All together we call it as a population. Chromosome representation, as I mentioned, it will be represented only zeros and ones. And the chromosome contains the genetic information that define a particular solution. So the line, whatever you are representing ones and zeros, that consisting of the genetic information of that particular solution. The next terminology, fitness solution. So what is the fitness? Suppose for it is a real coded genetic algorithm, let assume that your function is equal to x1 plus x2. Let assume that the population we taken two variables, no, this is x1, this is x2. Randomly if I take some values, and then what is the fitness, these x1 x2 values you can substitute here, 3 plus 2. That is the way to substitute in the real coded genetic algorithm. But here suppose if I consider as a binary coded, then x1 you take it as a some chromosome, x2 you can take some chromosome, like that a number of populations you can take it. Here population, suppose you can consider 0 1 0 1, suppose 4 bit operation if I do, and x2 also something you can take like this. And this is the one chromosome. The totally for one solution, this is a one chromosome. Like that, you can able to make use of this is the second solution, and you substitute this value or converted into real value and substituted here, that will get it as a fitness value. So like that, there is another parameter. You remember it is a fitness. It assigns a fitness score to each solution based on how well it perform in the solving the problem. The higher the fitness score, the better the solution. So obviously, whenever we can see uh, more fitness means best solution. That is the way we can identify which one is going to be as a better solution. So in that case, we can observe while we are selecting the solutions, which one is the better solution. Like that, we can easily identify. And then selection. So in the selection phase, individuals with highest fitness score, because it is not a one step of solution, we need to repeat that problem continuously. That is the reason higher fitness score are more likely to be selected for reproduction. So what you'll do is, suppose some 10 populations you generated and you calculated the fitness. Some of the population or chromosome solution, or you can say that indeed candidate solution fitness is minimum, then you can discard that. We will not forward to the next iteration process. While you are selecting, there is a different kind of processes are there. At moment, what I'm telling is, with highest fitness score are more likely to be selected for reproduction in the next process. That again in the from that best solution will carry forward next and again. So if we do this, finally whatever solution we are going to obtain, that will be as a best solution. And then crossover. During crossover, pair of selected individuals exchange the genetic information to create a new solution or a new offspring. Suppose the first chromosome, let it be as a some values. I can say some just for number I'm giving 10011. This is the parent one, and parent two, it may be like this. So now, while you are doing the crossover operation, we need to pick up minimum two solutions, or parent one and parent two. Then you have to perform the crossover operation. It may be different kind of crossover operations are there. I can say that single point crossover or multi-point crossover and so on. And here, suppose at any position you want to do the crossover, or suppose if it is a 2 point crossover, and these things, what will happen? These information is going to exchange between this. This is the point one, point two, and between that, the new offspring is going to be offspring one, offspring two will be generated. Here is a parent one, here is a parent two. By doing this crossover operation, offspring one will become the before this crossover points as such you can write. This is the offspring one parameter one. Here 0 0 in the lower side will we make it into upper side will make it into lower. So now what will happen? 1 1 0, and this will be remains 1. And like this is the one offspring, and another offspring will get it. This starting is 0, and then this upper side will come into the lower. So 0 0 1, and last one is as such 0. So these are the new solutions or offspring by doing the crossover operation, if it is a 2-bit crossover operation like that. So we have multiple that I will explain the next topic of that. Now I'm trying to explain what is the sequence of this genetic algorithm will works, and in turn there is in each step we may have as a different kind of operators. Now This analogous to genetic recombination in a sexual reproduction. Suppose two parents, then after that new childs will get it, and again in the next generation, the different kind of the people will do the crossover operation. Then new solution will arrive, and then that means what where genetics is going to be exchange the to get as a best product, or the generation to generation how people will get the knowledge or skills will be more and more. That is the scenario here. Different crossover techniques, 1 point crossover, 2 point crossover, and uniform crossover can be employed in this operation. We'll see while we are solving the problem whether we'll go for 1 point crossover or 2 point crossover or uniform crossover, like that. Another operation is a mutation. Mutation introduce random change to the offspring genetic information. After getting as a offspring, and then in mutation operation, one of the genes is going to change. Suppose if it is 0 is there, you make it as a 1, or 1 is there, you make it as a 0, like that. We can do the mutation operation, the mimicking the genetic variation in the natural evolution, and it helps to explore new regions of the such space that might not be accessed through crossover alone. Then finally, termination conditions. So as I said, the termination condition, the predefined number of iterations we have to proceed this operation. What are the operation? The crossover and mutation operations we have to do continuously by fixing the number of what you call it as iterations, or until termination condition. You can write your own termination condition. If that parameter reaches to that value, then the process we can stop. That is what the termination condition. Reaching the stationary solution, or exceeding a specified computation budget. So whatever uh, any condition, these are the some of the conditions we can stop the programming part or calculation by using this termination condition. Then replacement. After generating offspring, offspring through crossover and mutation, the next generation is replaced to previous one. Why we need to replace? By seeing this total scenario principle of genetic algorithm, what is happening? Initially, we are generating random population. That is the first solutions within a boundaries, or within a minimum value and maximum value of the individual variable. We are generating the random population that we can pass to the fitness. Then the fitness which is having more fitness, that will be as a best solution. Then we'll go for as a crossover operation. Then we can able to uh, get it as a mutation. After getting as a mutation operation, we'll do this process up to the termination condition, and finally we'll have as a replacement operation. So this process is going to continue to get it as a final value. Some individuals from the current generation may survive based on the value of that, whether it is a best solution or not, in the next generation. So once the crossover mutation is happen, we'll see that whether it is a best solution or not. If it is a best solution, we can replace that. Mm, and based on the selection criteria, ensuring that population evolves towards the better solution over time. And we'll see same. That's what principal operation. We'll see the working of genetic algorithm also in the same manner as usual. Initialization, What will initialization? Generate a initial population or candidate solutions randomly or using specific techniques. Generate initial population of a candidate solutions randomly. That is the first step. Then you have to evaluate. As I mentioned, these variables are random solution. You can substitute it in a function. We will get that we call it as a evaluation and fitness. Let it be. If the highest fitness is more probable to go for as a next solution. Then selection. Selection individuals from the current population based on their fitness. You can see the sequence. First random generation, that values or solution substituted in a function, you will get the function value, which is having as highest fitness. You have to calculate the evaluation process. That is nothing but you are calculating the fitness and highest you know fitness value will be the next generation. That's what selection. Individuals from the current population based on their fitness scores to create a mating pool. So for the to do the next operations, what you can do is selection process. We have the different kind of selection process also because we have different solutions. Let it be as a these are the solution. We'll go for as a meeting pool. What we'll do is tournament selection, like that. These two players will play, and who is having the best fitness. That suppose one, two, three, four. These are the four solutions we have. Randomly, we'll pick up these two and select which one is the best one. That will make it as a here mating pool. This is a we can write as a mating pool. These two will compare. Suppose this fitness is more and this fitness is less, then the first chromosome will come to the mating pool. And you compare these two, and when you are comparing these two, suppose this may be best fitness than this, then you can write as a 4 is a in our mating pool. So like that, we can able to select the populations. And after that we selected these two. Like that, if the solutions are more, no, suppose 100 solutions are taken, populations are 100, then mating pool, what you can write, you are comparing to two and which is the best, that you can make it as in a mating pool. Then therefore you will get it as a 50 chromosomes in the mating pool. For that 50 only we are operating as a crossover operation, not for what you call it as previous all. So what we will do only after selection, that 50 if we select based on that, still not only 50. Sometimes if tournament selection, if we consider as a 3-3 comparison, then among the three only one will be selected, and again another three you can select. Among three again one may be selected, like that it may be reduced by 3 also. That is also possible. Or preferably K tournament number is 2. You can take it for the best selection. So that is also possible. And crossover operation. Apply the crossover operation to pair of selected individuals. Now what I mentioned here is a some solutions we selected. 2 you will take it, and from that you can single point crossover or 2 point crossover or uniform crossover. You can operate any of the crossover approach and to get as a offspring. What we'll do, you are taking as a two parents here, we are performing the crossover, two offsprings will get it, like as I shown you in the previous. That is what crossover operation. Then mutation. What we'll do, introduce random changes in the offspring genetic information based on the mutation rate. Suppose you want to change after offspring, You can take it as a randomly one of the gen is you can change the operation point, and then that we call it as a mutation operation. After that, replacement. How we can replacement after doing all these crossover and mutation operation, we create a new population by combining the previous one and offspring one. They can see that combining the offspring after doing this two crossover and mutation, we can able to get it as a offspring, and some individuals from the current population, everything you can write it here, and you can select the which one is having as a best fitness, that we can go for as a next solution. Sometimes after crossover and mutation also, previous solution may be better than crossover and mutation. You can retain the previous solution. If after crossover and mutation, the solution is better, new solution is better, then you can take it as a new solution. Like that, greedy selection is going to be takes place to carry forward the next process. This is the working of a initial steps: initialization, then evaluation, the selection, crossover, mutation, and replacement. And then termination, the repeat the step 2 to 6 until the termination point reached. What is the termination point? As I mentioned, if the number of iterations we predefine, this process will repeat from second step to the sixth step continuously. Once that number of iterations are reached, then you can stop what you call it as a process. Now, this is the flow. Many literature will show the different flow charts also. I will show 2, 3 flow charts to easy understand. Everything is same only, but we can observe whatever working procedure I mentioned here, workflow, same we can see. First, what we have is a population. So, some population we have here, something some n number of populations. Then tournament selection. So how we get the tournament selection? After getting population solution, we are finding the our evaluation or fitness. We are finding the fitness of the solutions. That's what the process you can see, the initialization, then evaluation. Initialization is nothing but a here population or a solutions, then evaluation, then selection process, crossover, mutation, replacement. Same order you can see. We can observe population, then we'll get the fitness. So we'll go for as a selection process. Next, after getting as a fitness selection process, this fitness value is 1.5. This fitness may be 3. This fitness may be 4.2, and this may be 1. Like that, we have as a different fitness. Like this, you may have n number of populations. Now, the tournament selection meaning is what? Tournament is nothing but the two commentators they will play. Suppose cricket match, two countries they will play, and one will win. That is only the tournament selection. So these two guys will play the tournament, and one will win. Who will win preferably? Who is having as a best fitness, that we can write it in the mating pool. The next step is a mating pool. So there is a, I can write this mating pool that 1.5 first solution, second solution is 3. We will come to this 3. This guy is a one mating pool. Among this 50, you will get only 25. Suppose if you take populations are 50, you can get it only 25. Like that again, these two you can compare 4.2 and 1. We'll take it as a 4.2 solution in the mating pool. And another 2, maybe next one is 3. Like that, there is a next solution, maybe 3. Like that, from the population, we are going to select. So using the tournament selection, like that, we may have different selection process. anything you can take it. Let in this I taken as a tournament selection, and we got the mating pool. So here 25 are there in the mating pool. After that, we have to apply the crossover. How to apply the crossover as per previous explanation? Two solutions you have to take it. Here maybe first solution this one, and second solution maybe this one. These are the two parents, and perform the crossover operation. It may be 1 point crossover or 2 point crossover, like that. Suppose this 3 is a real coded, but actually binary coded 1 0 something, some values we can, whether it is a 4-bit solution or 5-bit solution or anything, we can take like this. Suppose if I take 1 point, the or 2 point, that other bits is going to be exchange each other. So once that is going to be exchange each other, what we can do is new offsprings is going to be happen after crossover operation. So now you can see, to like that we have to take it as a two parents and perform the crossover operation. That is a parent solution. Then perform the crossover operation, exchanging their chromosome information. Then we can see a new solution or new offsprings will get it. This is the next step of strings. After that, there is a mutation. So by taking the offspring, randomly pick up the any of the bit, you can modify that bit. That is a mutation operation. So after that, again, after exchanging this or changing that mutation, we'll get it as a offspring. This offspring will go for as a survivor. So what is the survival here? Now you can add population and offspring together, because here we taken as a 50, and again which one is a better, we will get it as solution and will perform, and finally final offsprings add with the population, and together we'll select which one is having better fitness, that solutions will take it. That is the new population. Now after doing that, again we'll give it the initial step. That process continuously repeat until it reaches to the what we call it as stopping criteria. And this is the basic flow chart we can able to perform. And similarly, some other same thing only, but we can make use of this way also. Initialize and evaluate, then this population will be there, and then it will go for selection. What is the selection? Based on the fitness function. Best fitness is going to be select, that we call it as a parents. Then there is a two operators we need to perform. One is a crossover operation and mutation operation, and if we perform these two things, we'll get it as a modified offspring, and then we can evaluate that. We'll go for as a new offspring, because after crossover and mutation we need to evaluate for the new fitness and compare with the old one, and which one is going to be retained, that we have as the highest fitness, that is a new population. That cycle is going to be repeated, and if it is reaches as a criteria, or let it be as a fitness is very less, we can discard that solution, or it will pass to the next iteration. So like that, there is another way of flow chart, or still you can see the same, whatever the workflow I mentioned, that only we can represent as a uh, way of flow chart. What you can do: population, initialization, the fitness function, then crossover, mutation, then selection process, termination process. That loop is going to be repeated until the termination process condition met. If that termination is reached, I mean criteria is reached, then that you can stop it. Same thing, we can write the program part. genetic algorithm initialize the population, first one, then find fitness of the population. Then while this condition is a termination condition, you can mention the iteration count is equal to 100 or 200 or 50. Based on that, you can write the termination criteria is reached. Then what you can do is parent selection, crossover with probability. What we have to select as a parent selection, we are doing the crossover. How to do the crossover? There is some logic also you can do it. Mm, Crossover probability, mention it, randomly generate that one probability and compare these two, random is r, and these two we can compare, and based on that crossover is performed. Similarly, mutation also, pm is nothing but a mutation probability, and pc is nothing but a crossover probability, and based on that you can perform the mutation and crossover. And and decode and fitness function, because all will be as a binary coded, we can convert that into real coded, and then we can find the fitness calculation. After that, survival selection, then go for as a best solution for the next iteration. This also is anything, any one, preferably you can use this one. It is a simple way to find the loop, but you can make a one condition, if condition also, if that criteria reached, or stopping criteria is reached, if it is yes, terminate the solution, if it is no, repeat this loop continuously. That is only the process. Now, we have some advantages of genetic algorithm. That is a global optimization. That is nothing but a genetic algorithms can efficiently search large and complex solution space to find globally optimal or near optimal solutions. Then the parallelism is also possible. These are some advantages. Genetic algorithm can parallelize, means the calculation we can do it parallelly, allowing them to exploit parallel computing architecture. That's what the parallelism. Another one, flexibility. They can handle various types of optimization problem, whether it is a complex problem or combinational problems, or including continuous discrete problems. Like that, we can able to perform the genetic algorithm with variety of the problem. Another one is a robustness. These algorithms are robust against local optima. Then their stochastic nature, means the random in nature, and the diversity of the population. This is the robustness, and we'll see some applications of genetic algorithm as well. There is a engineering design problem. There is optimization of complex systems and parameters in engineering design process, and machine learning, feature selection, parameter optimization, and neural network. For that also, we can use this genetic algorithm. Economic and finance sector, they are using this genetic algorithm. Portfolio optimization, forecasting, and risk management. For such kind of applications, we can use as a genetic algorithm. Another one is bioinformatics, sequence alignment, protein foldering prediction, then gene expression analysis. This kind of bioinformatics we can use genetic algorithm. Robotics also, because path planning. What is the best optimal path to reach the destination? Using the robotics analysis, or you can see that for in robotic application, we can use genetic algorithm to find optimal path. That's what the path planning, control optimization, and robust motion planning for us kind of. Now, again, still we'll see some more what you call it as genetic algorithm individual steps with small example for that particular step. What are the steps we have? We have seen the flow, genetic flow, initialization, then fitness, then selection, then crossover operation, mutation operation, and finally offspring solutions will get it. And for new selection or surveillance. This is the process. That's what there is some terminology we already discussed. There is offspring, new generation generated solutions. We call it as offspring, and parent solution from which new solution is generated. So this is the initial, then offspring after performing the G operators will get it as a offspring. Offsprings are generated through reproduction and mutation and crossover. That's what the reproduction is nothing but a selection of good solution for mapping, mating, and the variation, crossover and mutation. Selection of good solution after variation operation. Better candidate has more chance to survival. Suppose if any solution is having more fitness, that solution is having more chances in the limited resources. Good solutions are retained and bad solutions are eliminated. Now we can see how one small each step. I'm going to explain one small example how we are able to perform. Once we are aware this, finally what we can do is we can able to use one example and we can solve this problem. Now, first suppose there is a one function is there with minimum and maximum conditions, x minimum and x maximum. You can see x minimum and x maximum. For that, we have to generate a solution. After that, how to calculate the real number also. Now, what is x minimum in this problem? We can take it as n is equal to 5 is given in problem, that is in our choice. 5 bit we have to take it or 4 bit we have to take it, that sometimes problem they may specify. If not, you can decide your n value and project x minimum value and x maximum value. Suppose x minimum is 0, you can put it all parameters is a 5 bits will be 0, and x maximum, how much you can get it for the maximum here, n is equal to 5. All these bit analysis, 2 power 0, 2 power 1, 2 power 2, 2 power 3, and 2 power 4, like that. And if we make it as a ones or zeros, we can easily calculate value. This is the way. Suppose if binary values are 1 0 0 1 0, then what is this value multiplied with 2 power 0, this value multiplied with 2 power 1, this value multiplied with 2 power 2, then 2 power 3, 2 power 4. That only is happened in the calculation. So what is happening? 0, 2 power 0 is 1, and we'll get it as a multiplied with 0, solution is 0, and 2 power 1, then 2 power 2, 2 power 3, 2 power 4. Like that, if I calculate, I can get maximum for this binary bit 18 is a value. So that is what decoded value. We are going to decode the value of binary value. Like that, this is the formula decoded value, or in general without formula also, very simple logic. Whatever, suppose this, what is decoded value, I can write this is all 1 into 2 power 0, all 1 into 2 power 1, 1 into 2 power 2, 1 into 2 power 3, and 1 into 2 power 4. So just 2 power 0 is 1, 2 power 1 is 2, and 2 square is 4, 8, 16, and so on. You add all the things, we'll get it as a what is the decoded value. And now, if we want to calculate precision, this is the formula, or real value I want to calculate, you can use this formula. If n is equal to 4 or 5, you take it. Depends. 4 bit you want to operate, or 3 bit you want to operate, or 5 bits you want to operate. Use the formula. For evaluating the fitness, as I said, first step itself as a population, then next step is a evaluation of the fitness. So will you get the fitness value? Consider minimum value is 30, I mean 5, maximum value is 30. Use the 4-bit solution how to generate as a population. So what we can do, 5 is minimum, maximum is 30. Use this formula to get as a real value. So in that x minimum is 5, because using this formula I'm writing 5 plus what is your precision? There is x max minus x minimum. So 30 minus 5 divided by how many bit here? Dimension is a 4 bit. So 2 power 4 and minus 1. This is the x minimum value 5 and precision formula, and then decoded value. What is the decoded value for the first population? Suppose this is the first population. How can you decode it? For the binary of 0, 1, 1, 0. What is decoded? You can see 2 power 0, 2 power 1, 2 power 2, 2 power 3. So this 4 plus 1, I mean 2 power 1 is 2. 4 plus 2, 6 is your decoded value, and multiply 6 here. So then that will give as a new solution. So you got it as a 15. Like that, each population you can perform this value of the fitness, which is having more fitness, that will be as a good one. That is a binary coded genetic algorithm we are going to perform. So this is the second one. And now like that, based on the n bit, 4 bit you can use it, 3 bit you can use it, 5 bit you can use it, based on the maximum value x maximum can decide. Now suppose for example n is equal to 3. If I taken as a bit 3 bits, 2 power n. What is 2 power n? 2 power 3. That is a 8 possible solutions. Suppose you need more possible solution, we can increase the bit as well. Now for that binary, you can make use of 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, like that. You'll get the finally 7 and 0, the totally 8 solution. This we call it as a population. 8 population. So how will you get the actual? As per the previous slide, actual you have to use this formula. Using this formula, we can easily find the actual solution. So we can see x minimum is 5. That's what I mentioned. Then precision, because this minimum minus maximum divided by 2 power n minus 1. That is a precision. So that precision is a 3.57 into decoded value. What is the decoded value for the 0, 0? All three zeros decoded value is 0. So therefore, thus we can write it as the actual value is 5. And for the next population, you can see actual value. What is the actual value? Precision we already calculated, because this is a fixed one, 3.57. X minimum is 5 plus precision value is 3.57 multiplied by decoded value is 1. Then we can see this answer is 8.57. Like that, you can calculate all the actual value. From this, which is the best solution? Who is having as a more fitness, that we can get it as a best fitness, best solution. Now similarly, I say minimum and maximum, I want to generate as a different population with bit size is, let me as a 4. 2 power 4 is a 16 possible solution will be generated. In that 16 possible solution, I wrote this 0 to 7 and 8 to 15. These are the order in the same. I mentioned after this table, same continuation. You can represent this table here also. We'll get it as a 15. I mean total 16 solution. In that 16 solution, each binary bit you can decode it. You'll get it as a, all these like this. Then actual value you can find based on the formula is mentioned here. From that you can see precision is going to be improved if I using the bit size from 3 to 4 and 4 to 5 also you want you can check it, that is also going to be improved further. And same flowchart, we'll see this example population, initial population. How will you get the initial population? Let the n is equal to 6. I want to generate initial population variable, two variables I want to use. Suppose f of x is equal to x1 plus x2. How to generate as a initial population? Instead of this function, you can make use of your own function also. We can easily generate. So now first initial population. How many I want to generate? Suppose 6 I want to generate. For x1, you can use as a 5-bit solution. x2 also you can use it as a 5-bit binary. Now let it be randomly. I'm generating some solution. This is for first population. Similarly, second population like that. You can generate 6 populations. Or other version, the bit may not be uniform, equal n bit may not be required. Suppose here is a 5-bit, here also 5-bit, randomly we are generating the ones and zeros. But some problems, or you want to change, here may be some bits and here may be another number of bits. So like that, we'll get it as a population. So once if you are getting as a population, and you can see this is the first step. After that, what you have to do, identify the good solutions, eliminate the bad solutions. Then we will go for as a reproduction. Now for that, what is happening? We are go for as a tournament selection. As I mentioned already, tournament selection, you have to convert that binary to the real value and let it be as a 4 function values. K is equal to 3. If I take tournament 3 3, you have to perform. Suppose here you can see 6 no, you can able to take any random 3 solution, which one the after calculating is a fitness, which solution is having first one or third one or fifth one, because I taken randomly these 3, which is having as highest fitness, that you take it as in the mate pool. Like that you can take 2 2 also. Let example 3 I taken, the function I taken fourth one, second one, sixth one, let assume that fourth, second, sixth randomly I picked up, which is having highest function, that will, because maximization problem or minimization means lowest function is the best one. In that, what will happen? Total 6. No, if I take 3 3, only 2 will going to be win. Or if I minimization problem solution, 6 is going to be win. So like that, we can easily mention this type of the tournament. So this is the selection of the tournament, and we'll see this in the next class, just continuation of this first class, maybe some other class we may have. If you have any doubt, you ask me, otherwise you can leave. Yeah.